Hello, I am Sara Haravifard. I am a physicist and a material designer from Duke University. I am interested in tailoring materials that have a specific behavior. Eventually, other scientists and engineers will utilize what I do and turn them into technological advances. But my job is to be at the front line of discovery. Theorists predict compounds that will have interesting magnetic behaviors under certain conditions. I design and synthesize these compounds in my lab at Duke University, then take them to places like the MagLab. With my collaborators there, I look for what actually happens at the low temperatures, high pressures, and high magnetic fields, where exotic behaviors are predicted to occur. I use the magnetic field as a probe to tune different states of matter, to push them from one state to another. Then I study those phenomena that can emerge only at those transitions. I study so-called frustrated systems, which are magnetic materials that cannot magnetically order. Due to their geometry in the crystal lattice, the electron spins cannot all align even at very low temperatures. For instance, consider the triangular arrangement in the crystal lattice, where the interactions between spins is antiferromagnetic. At any given time, 2 of the 3 spins can align in opposite directions without any problem. But the third does not have a partner and becomes frustrated, not knowing which way to point. Because of this frustration, the spin wants to be in numerous states at the same time and tries to find the one state that is going to make it relax. By relax, I mean that it could have the lowest energy because all compounds want to get to the lowest energy. Under the right conditions, this frustrated state can yield a novel state of matter called quantum spin liquid. The unpaired spins in quantum spin liquid, although are disordered and pointing randomly, are still communicating with each other. There are special quasi-particles that go between these spins, and instantaneously they can figure out what the other guy is doing. So this entanglement between the spins is what makes it very special and a possible material for quantum computing. This past summer at the MagLab, we discovered a new state of matter in the frustrated compound strontium copper borate when we applied pressure, low temperature, and high magnetic fields. We discovered an area of the phase diagram which had not yet been reported. It is called 1 out of 5 or 1/5 state, which is a unique crystallization where every 5 bosonic units in the crystal is different. It is actually very much related to Bose-Einstein condensate. The underlying physics is similar, but you have 3 tuning parameters: magnetic field, pressure, and temperature. And you can tune the bosons in these crystals, which can lead to a lot of rich physics. Theorists had missed this new phase of the material, so they took our new findings and reviewed their models. Then they proposed a new phase diagram that now captures what the experimental data has shown.